Jai Hind to all. My name is Aarti Chaudhary. I'm as an assistant professor in AKGEC Engineering College, and today's topic is asymptotic notation that is used in data structures also and in DA also. Okay, let me introduce first to the asymptotic notation. Before that, we have to go into the what is algorithm into that. So before going to algorithm, what we have to do is we are having any problem. We are having any of the problem which we are facing CS or IT branch. So that problem has to be having any solution for it. So to solve any problem, what we have to do is we are having a program of it in any of the language, in C, C++, Java, any of the language, what we are having. So for example, in C, we are having a solution for that problem. But for that problem, what we have to do is, before going to a problem, before going to any program, what we are having a informal description of any problem. So that is a blueprint. So before going into that algorithm, program part, we have to first go a blueprint of it. That is a blueprint. The blueprint, or maybe you can say, is informal description. And any layman also understand that this is a problem and this is a solution for it. So that is informal description. Fine. Before going to that, so for example, we are having an informal description that is called a algorithm. So before we are having a problem, to solve any problem, we are having a algorithm, that is infinite description of that part. Okay, we are having a A1 algorithm, for example, A2 algorithm, A2 algorithm, A3 algorithm. We are having many of algorithms. We are having A1, A2, A3, A4. We have to select any of the algorithm. But what is the criteria to select any of the algorithm? So these are the two parameters, that is the time and the memory. So for any problem which we are facing, we are having many of solutions, that is many of algorithms for it. To select any one of the algorithm, what we have to do is, we have to select an algorithm, and for that algorithm, we have to make it possible that that algorithm has to be have minimum time, so that is you guess fastest time. In fastest time, what we getting a solution for any of the problem, and in the less memory, that is less. So these two problems are addressed by a time complexity and the space complexity in that field. So we are having any algorithms, we are having many solutions for the problem. We have to select any one of the problem, and any one of the problem algorithm which is having a fastest algorithm in minimum time, that is deliver a solution for it, and in the less memory time, that is in a small memory we are taking and we are having a memory of memory taking is less. So we have two criteria for selecting an algorithm. First one is we are having a fastest time, and second one is we are having a less memory. So we are having a problem, we have to make a solution for it by using any algorithm. That algorithm have to be chosen such a way that it is a fastest, having fastest time. In overall other algorithms, it is taking a less times, and we are taking a less memory for it. Fine. The next we have what is asymptotic notation. What is the need of asymptotic notation? To give a need is, asymptotic notation has to be a mathematical foundation and framing of any algorithm. So we are prepare any algorithm. First we have prepared any algorithm. We are having a runtime performance of it, that is our time. Just we have seen in a previous slide that time complexity has to be bounded by any asymptotic that is framing of that is done by using a asymptotic notation. So we are having for any algorithm, we have designing an algorithm, we have to be cases of, that is best case, average case, and the worst case. In the best case, that is the minimum time, better than that is not there. In average kind, in average time, it will taking this time we are having in the worst time, beyond this time, beyond this not exceeding that time, we have to be there. So we have to be worst case also, average case also, and the best case also. This is the making that if the asymptotic notation is having an input size, so it is dependent on the input size. What we're taking our input, and then the input has to be 0. If the input is 0, then it is a constant time. If we are having a constant time if there is a no input. If it is input, so it is dependent on that input we are having. ठीक है, asymptotic notation is to be a running time scenario. It runtime algorithm, how much time it is taking by using a time complexity, that is analyzed by the asymptotic notation. ठीक है, asymptotic notation has to be of three notations. What we are having is big O notation, big theta notation, and big omega notation. The big O notation, we are making a big O. In a theta notation, we are having a theta, and this is we are having a omega. We are having that. Okay. The first we have to consider our first big O notation. What is big O notation? It is also called as a tight upper bound. How this name arises, I will let you know about that. So by using this graph, first we have two axes. That is one is for time and one is for the input. What input size we are taking? N. So this is our input size. We are taking our input size, and this is at this time we are having. So any function that is any function we are taking that is taking any according to size, it is growing like this. That is called a fn. At time increases, at the input size increases, it is growing like this. F for f of n. So what we have to take in a big O notation, what we have to make that a person that the function having a upper bound of it. Upper bound is कि maximum not exceeding that. Fn function, there is some complexity of that time complexity of that function, maybe n square, anything, because it's an algorithm. So it's a algorithm in runtime performance also, it is having a time complexity also. That time complexity has to be making that sure that upper that down. That is, we are having a CGN function. We are any other function, that function making a upper bound of that given function fn, so that exceeding that time it will not taking in our runtime scenario. That is, we can also say in a worst case scenario. So big O notation indirectly says the worst case scenario of it. Okay, in the worst case we are having a this performance, after that it's not exceeding on that. Fine. So we are having, and what is this n naught? After this n naught, we are having our inputs of n. After this n naught, the this function is always a below, and CGN function is always a big function. So it is always upper going like this, and this fn function is going like this. Okay, every time. So we are having in a big O scenario, we are having that fn has to be less than equals to C of G of n, because it is giving a upper bound. So it is always upper in that, and C is any constant by a 1, 2, 3. So C is always to be greater than 0, maybe also 0 also at that time, not 0, because it's greater than 0. And at this n naught is always greater than 1. 1 is n naught is ki always we are having a only, because I am saying that asymptotic notation is bounded by a input size. So that is, input size has to be always 1. We have to give always one input. So at least we are having a one input of it. Fine. And n naught hamesha we are having a n naught is greater than equals to n, n is greater than equals to n naught. So we are having a notation of that ki fn function is less than equals to C of G of n. This is a function where C is any constant which is greater than 0, and n naught, at situation of n naught arises, any n naught, 1, 2, 3, 4, any situation. I am giving also example of it. At any n naught situation, this will go that the fn function will be always smaller, is always low than the CGN function. Fine. So we are giving an example of it. In this example, we are considering a function of 3n plus 2. The function is equals to 3n plus 2. So I can also write that is this function is big O of g of n. Is it right or wrong? We will check it out here. So a fn function and then the gn function is to be n. So we will take a situation that with 3n plus 2, this is a situation, and where c of g of n is that is n. Okay. When we have a situation that 3 of n is to be less than equals to, that is to be c of n. For that c of n, this part has to be greater than this part. So what we have to consider at this situation, that is c. What is a value of c will be? Maybe that is also 4. We have having a situation that c is always to be greater than 0. If we take 1, no. If we take 1, it will make a small, this part is greater, that we don't have to make it. Make it 2, no, we don't have to make it. 3, it is equals to, because, but there is some constant part. So in the safe side, we are making it c equals to 4. So that c equals to 4, so making that 3n plus 2, and we are having a, this is equals to 4n. So this situation arises where 4n has to be this part, that is c of gn has to be upper bound of 3n plus 2. So my function is going like this. My function is going like this. So this is 3 of n plus 2, and this is my 4n function. 4n function. Okay, my function is to be 4n function. So at any point that my function is always down at n naught point. The n naught is, importance of n naught is before that maybe my function will be higher, but at the point of n naught my function has to be, fn function has to be lower than the cgn function. That is a big O notation mentioned. So by making that, we have to be the n values also, n naught value has to be greater than equals to 2. So by making that, by making c value 4 and n naught value is greater than equals to 2, at this situation my function fn is to be big O of gn equation. That my function fn is a division. So it's correct. Yeah, we will make it this correct. Next, we are proceeding to the other notation, that is big O omega notation. But omega notation is reciprocal of it. It is giving a upper bound and it is giving a lower bound of it. But by making it, what we have to be, the function has to be, this is 2 lines we are having, this is an input line, this is a timeline, we are having a function of, this is fn, but fn function is like this, and we are having other function because we are making a situation here, we have making a lower bound of it. So any function which are having a lower bound, that is cgn, before that my function is taking any time to make it that possible, that function is giving it time, but the cgn function that below that, better than that, is not possible. If a algorithm is taking this time, or this is big omega time, this is a bestest, because before better than this will not take this. So we are having a function, this is fn function. Fn function has to be greater than equals to c of gn, and we are having a situation where c is also greater than, same as big O notation, c is greater than 0 and naught is greater than equals to 1, and n is to be greater than equals to n naught. That the situation is. We are having these three constants, same as big O notation, but we are having a seriousness, that is fn has to be greater than equals to cs. That this is so it is giving a lower bound. In the previous side, what we are giving a, that is a this. So this is given a lower bound of it. Lower bound. Okay, so we are giving a lower bound. Better than this is not happening. In the big O may we are giving a tighter bound. This is a worst case scenario. It is run in this time complexity. This is a situation. Same question here arises here when we are having a fn function and gn function. Fn function is 3n plus 2. So we have to check this. Okay, is this function has to be omega of g of n, then we have to check is fn is less than equals to c of gn, because it's a situation where c is greater than equals to 0 and n naught is equals to greater than equals to 1, whereas n is greater than equals to n naught. Fine. So we are, this is 3n n plus 2. we are having this, and this is C, and this is N. So what with this is greater. This is always greater. So by assuming that C is equals to 1 and N naught equals to 1, so we are having situation that N naught equals to 2 is always greater than this is N, and this is situation. So at this situation, this we are saying that we are having a function which is always this part, Fn part is always upper than the CGN part. That is at the C equals to 0 and N naught is greater than equals to 1. Procedure. But what about this? Can I write it Fn is an omega of g of n? Is it correct? 3n plus 2 or greater than equals to c of n square? Can we write? Can we substitute any value of c here that this part will become a lower than this part? No, so we can't write a function of this is here because it is exponentially that is polynomially. We can't put polynomial here. This is a restriction of C. This C is always a greater than equals to 1, but it's not polynomially multiply. So we can't write n here because we can't write n square here. So we are making that this part is always, if I put it 1 also, this is n square and this is 3n plus 2. This part is always greater. Without making it 1 also, this part is always greater. So can I write this is in this form of this? No, we can't write it. That's why this is not a Newton. But can I write a big O here? If I say this function is big O, is order of big O of g of n, but just put it down 3n plus 2, and this is this c or g or n square. So we are having a situation that this is greater than equals to, yes it is. So we can write a big O of here but not the big omega of here. Fine. Okay. Next we will go for a big theta notation. It is a notation where we are giving a average because theta is average. So we are any function which is here, Fn function, we are making a upper bound also and lower bound also. So we are making a, by using a C2 we are making a upper bound, and by making a C1 we are making a midpoint. We are making a function that it is bounded by lower also, bounded by upper also. But at any n naught time where n naught is greater than equals to, that is for the all the one greater than 0 and n naught is greater than equals to 1. Fine. Next, this is the big O notation. Can I write for this also? That Fn function is theta of g of n. I will write it down. That Fn function is 3n plus 2, and we are having a equals to for c of g of n. But we are having a situation where we are bounded by 2, c1 and c2. So for what we have to make it, that's for the c1 also. We have to make it the 3n plus 2 is equals to c1 of n. To make it upper bound also, lower bound also. So if we are having a function like this 3n plus 2, so it is also bounded by upper also and bounded by lower also. So that is how much value of the c we have to take it to make it a upper bound, and how much value of the c we have to take it for the lower bound. So what for the upper bound, what is c1? C1 have to take is 4. So for the 4 value, we are making that upper bound. For the lower bound, we have to make it 1. So for example, we have two cases. C1 is equals to 4. The C1 equals to 4. 3n plus 2. That is to be 4n. So that value is to be greater. Yeah, it is to be greater. Has to be greater. So that is the upper bound for it. Or agar C2 is value is to be 1. What we have to take is 3n plus 2. And we have to make it a n. So that is also the case. So we are making a 2 bounds here, upper and the lower bound we have to be there. Fine. So this is a 3 notation we are using, all because for any problem we are having an algorithm. That algorithm have a time complexity. The time complexity have to be divided in 3 cases. That one is a best case, average case and worst case. Best case is minimum that time required. It's better, not better than that. This is a better time we are having at the average case. The average required for the in maybe in best case, average case or worst case, they are taking a similar time. That is average case we are having. There's many algorithms which are taking in average, best case and worst case scenario. And in the worst case also, in the worst case that is not exceeding that. So in the worst case, in the asymptotic notation which we have done in the last 3 or 4 slides, the worst case is given by the big O notation. Fine. In the best case, we are given by the big omega notation, and the average case is given by the big theta notations. Fine. So we are the 3 notations we are having. So practically we are interested not the best time of it. We are interested in the worst time of that. Any algorithm, any problem arise, the algorithm we are designing for it. For that, we are designing the programs in the any of the language. We are interested in the worst case scenario. Worst case scenario, maximum time it will take to in a given input. What the worst time it is taking to run that algorithm in the runtime performance we are having. So big O notation, that is has to be there, which is more or less important, not the average or the best case. So in the down data structure, we are interested in the worst case scenario in the particle mention. For example, we are having a we have to calculate the mention. This is an array. It's an array. It's an array 1000. Maybe we can say is array of the integers. The 4, 6, 8, 2 bytes they are taking it. 10 and 12 we are taking this. Fine. How to calculate the worst case and the best and average case for it? So that cases has to be, if I'm thinking that it is taking a linear search. I have to search any element in an array, and we are taking a linear search here, for example. So we have to go and check, is it my number, is my number, is my number, is like this. Okay? It's a linear search. Continuously, we have sequentially we have to search about it. Okay, this is the cases. If I'm saying this, x value is 1000, 5, we can say it 5. So that is the first time attempt we are giving a value that is 5 at the first location we are getting it. The at this location we are getting it. This is a hit at the first location, that is at the order of 1 time we are getting. This is called a best case for it. At the first time we are getting it, that is order of 1. So is this when we are designing this algorithm and designing the program according to that, in the first case, if it's first number, that is at the starting position, we are get a hit and we are getting a best case of it, that is order of 1. Minimum that is better than that is not happening. That is a best case, and this is given by a big omega. This is a summarization slides you will get to know about it. X equals to, for example, we are having a 8 value. If the value is 8, and then after we have to check this element is present or not in my array. So I have to go in 5, then we have 6, then 7, then 11, 7, 1, 2, 11, and then 8. So we have to check every number. If we are having 1, 2, 3, 4, 5, 6, 7 numbers, we have to check 7 numbers. If I'm taking n numbers, we have to check n times. So that is a scenario. This is order of n time. We are making our attempt that at the order of n we will get the width. We have to from the start to the end we have to check it, and then afterwards. The worst case scenario means that we have to be look for the starting and then to the end. This is called a worst case we are having, and this is done by the big O. Big O. Exceeding that is not there. My algorithm will run into 1 to n time. Not n square time, not n cube time, not 0 time. No, it is restricted between our best time and the worst time. There's a best time is 1 and the worst time is n. In an average case, for example, in an average, if I want to find 1, so it will go into a log of n by 2, half of the time, because it's the mid of array. Mid, second last, second first, this is the element. So this is also equals to n. N by 2 is also n. So we are having a, what we are having a, this is a scenario where this is a big theta. Okay. This is an average case we are having, average. we are having an average case here. So in the slide, we have to be worst case, best case, and average case of an algorithm. We are having an array. In an array, we have to find any element by using a linear search. That is 5, 8, 1, all that elements we are having. So in the first case, that is our best case. At the starting, we are getting the element. In the worst case, we are getting not element in the first thing. With the end, we are getting, that is a worst case. Order of n time, this is not exceeding that time, we will get it. And in the big theta time is average case. We n by 2 times or n by 3 times, we are getting that solution, but is order of n we are having it. Okay, so this is a making a situation of the worst case, best case, and average case scenario. One thing more I have to discuss is in the big O case, what we are having here. Big O case, we are having something like big O case. This is a tight upper bound situation. Tight upper bound. In a big O, this is tight upper bound because we are bounding from the upper side. In the big omega case, we are bounding at the lower side. That is big lower, tight up lower case. But in the big average case, big theta, big average case, we are bounding from upper and lower. So in that case, we are having a situation where we are bounding for the best case. So in that, this is the best case. We are having a tight. We are having we have this big O time, the tight lower bound. And in the big case, this is a tight upper bound. We are bounding with tomorrow, that it is not exceeding this time. Lower bound, this is a better time we are having it. So we are just having it. So for example, I'm saying that fn function is to be a big O of gn function. Let's say in the past case, we are having this, and this is also c of g of n. We are making this. If it's 4n, can I say that it's if it's big O of n, big of it, maximum time it's taking like this. So if I say the big of n square also, big O of n cube also, we can say is 2n also. Yeah, we can take it. We can take it for 2n also. But the word is tight. Tight is for, that is tightest to the lower bound. So n say nearby is n square. N say nearby is not n cube, n4, and n ki power 2 ki power n. This is not tighter. So tightest matlab jo near, that is nearby to it. Okay, but in a case of upper bound also, if I'm taking a case of what fn function is to be of gn function, in this previous case 3n plus 2, we are taking that case, and this is n. So what we have to get tight, the tight lower bound, that has to be, lower bound has to be making tightest, not like log n, log n, yeah, log n. We are taking a tightest bound, that is n. So tighter is not, that is the nearest one we are taking is to be. Had to be nearest one we are taking in the tight upper bound also and tight lower bound also. So in any case, that is the 3 cases, best, average, and worst. The practical, we have to be interested in any algorithm which is taking a worst case scenario, that is big O, how much time it is taking, maximum that time we are not taking in any of the data structure and data subject. We are interested in the worst case scenario. Okay, so we are having this, and this ends our video, and thank you.